Hi, good morning, and welcome to the ZP Developer Zone. So we do this at 8 a.m. every Thursday at 8 a.m. London time, and I'll just jump straight into it. We've got about 9 questions a day. And if you have any questions, come to us on the ZP websites and just click contact us, and you'll always find that we'll respond to technical questions. And there's several sources of information at ZP. There's the ZP Academy. So if you're ever sort of wondering about this kind of science and engineering that we do at ZP, you can use our ZP Academy. We have our webinars. This, for example, is a free webinar that we do every week. And we have collaborations. It's probably worth saying today there'll be some talk on water and agricultural sensors. And those have come through collaborations. But of course, with collaboration, there always has to be some sort of, there has to be fuel. And one of the fuels that we found that's quite good is actually government funding, because coming off topic slightly, but water and things like agriculture, the margins are very different. The market's very set up very differently. So you often find that collaborations, you don't get so much private funding and private investment in those industries. I'll jump on a little bit more and say that we also post jobs through these websites. And we also have the ZP Developer Zone, and we also have workshops. And workshops will be important to today's discussion. So if you have any sort of technical queries, I think workshops are sometimes quite good as well. Now, with regards to workshops, we've actually had a workshop already this year. We had an online workshop just this Tuesday. And I want to say that in terms of workshops, we do have a lot of workshops. Most at the moment, we've got some set up in Grenoble in October. We definitely have some in Norway in February, and we have some in Swansea. Swansea in the UK, I should say, both in February and in January. So I'm just going to check that actually everything is streaming okay. Hopefully it is. We would ask you to like and subscribe if this channel is useful to you, but I'll click over that quite quickly and get into questions. Now, question number 1 was developing gas sensors, in particular nitric and nitric oxide, and we'll also reflect on carbon monoxide. Making electrical connections to gold electrodes, I will also touch upon that. Sensors for soil, I will discuss that. pH sensors, I will discuss that today. And I realize that the reason my this is probably not going so well is because I'm on the wrong. All right, so I've just actually changed internet connection because I was having actually on the wrong Wi-Fi. So I apologize for that if it's been poor so far. So I'll just recap and say that we will discuss gas sensing, nitric oxide and carbon monoxide. We will discuss making connection to gold electrodes. We will discuss also sensors for soil and as well. And we will also discuss pH sensors, and we will also discuss readers for uric acid, and we will also discuss screen printed electrodes and also Webstore items for CGM and Lactate sensing, also plastic and biosensors, and also methylene blue screen printed electrodes. So let me go a little bit faster into this. In terms of gas sensors, we do have what we call nitric oxide sensors. So there's quite a lot of data on the website, and it's probably worth saying that we're often making sensors that are kind of relevant often to the clinical range. So we have some nitric oxide data, and I put a link obviously to that. And we also have a carbon monoxide sensor. Now the reason I bring these two things up is because it shows that we do actually specifically test for nitric oxide, but in this particular case the person would like to detect nitric oxide in the gas phase, and that's not a sensor we have, though this carbon monoxide sensor is a gas phase sensor. So it's kind of, we're 50% of the way there in terms of we have a well, we have gas sensing capability. We just haven't done nitric oxide in the gas phase. And it just dawned on me how molecularly similar nitric oxide and carbon monoxide actually are. Anyway, that said, we do have experience with nitric oxide, but only in liquid phase, and we do have experience in the gas phase, for example, carbon monoxide. And any links, and I've put links, let's say, below. I just want to say hi to Martin and also hi to Hitcham as well. My apologies this morning for any internet problems. It's probably just worth saying in the gas phase, we do have definite jigs and rigs for setting up and doing gas phase type work. Just rather amusingly, if you ever want to do a nitrogen balance, for example, in a sort of farming situation, you have to both measure them. Sometimes you could actually do the measurement of nitrogens in the soil, sort of ammonia and nitrate, for example, but you could also then try and measure nitrogens in the gas phase above the soil as well. I think it's a bit over characterization of the situation, but that would be it would at least be an interesting study. Whether you can make money from it is a different matter. But anyway, we're talking about nitric oxide this morning, and we're talking about it in medical applications. So it's probably worth saying that, yeah, we definitely have a lot of jigs for actually being able to work in the gas phase. This is one of our engineers here. We've actually made a system where we're dosing gas in a sort of pulsed manner. Here we have a little chamber that we actually put gas sensors in. You can almost see all the mixing manifold for the different gases behind us. I can also see the alarms because we're dealing sometimes with even nitric oxide at high enough volume is it's laughing gas essentially, so it's not super good for you, let's say. We do have a lot of electronics. These electronics are used for measuring our sensors. There's almost like a generation 1 and a generation 2 sensor here, so I'll just move myself slightly and just say that these boards run our gas sensors. They also run a lot of our biosensors, but we've actually really miniaturized it down these days. So this little board here, which is about the size of my finger, no, sorry, the size of the tip of my finger, is a really useful little board. People ask what range of concentrations would the sensor be capable of. I think it's we can always tailor sensors to be within the desired range. There's all sorts of tricks, so it's in some ways it's sometimes easier to tailor them down to doing minimum amounts. You can always saturate a sensor with lots and lots and lots of sample. But that's generally not the case. Samples might be in sort of ppm, parts per million, tens of parts per million, but you don't really get materials that you're trying to analyze in that higher concentration. So when asked the question, what sort of ranges can you do? I sort of brought up this pheno. Pheno is obviously measuring the nitric oxide on the breath. And there, people are interested in the ppb levels. So I think we're quite comfortable with sort of going ppb, ppm. When you think about glucose, it's actually in very quite high concentrations of millimolar. But we tailor the sensors to the actual range. Most of the sensors that we make are actually designed to be in continuous use. So the question here is, are you capable of continuous gas exposure? I think when you look at the nitric oxide data, for example, and the carbon monoxide data, you will actually see that it wasn't just a discrete measurement, it was continuous measurement. So most of what we do in terms of nitrate sensors that we've made in the past, ammonium sensors that we've made, calcium sensors, carbon monoxide sensors, nitric oxide sensors, they're all designed to be continuous. You can use them for a one-off measurement, but intrinsically they're actually built to be quite continuous. The next question is a good question. The biggest, I want to say, thing in sensing sometimes is actually drift, and you can't ignore it. You have to characterize. You have to make the sensor, and you have to characterize that drift. And the question here is, would the drift be essentially in the zero signal? I think almost like the background, or will it actually be in the sensitivity? Yeah, it's a good question, and I think in this particular case it would be almost in the background signal. But of course, when we do have sensors that change in both parts. And the only way when you're making new sensors, unfortunately, the only way you can sort of find out is you have to make them, characterize them, and then you have to start fixing those kind of problems. We do things like finite element modeling to try and help us predict this stuff, but sometimes you might as well it's just as quick to make a sensor, and characterize it rather than sort of spend a lot of time necessarily modeling it and then finding out that the model, wasn't an accurate description, description of actual reality. The question here is, will something like measuring nitric oxide in the gas phase have a humidity cross-sensitivity? The quick answer is, I think most gas sensors actually do sort of account for humidity, so I couldn't see us really being different. I do understand the scenario that you could have a lot of humidity in there. I don't think getting rid of humidity is so hard. I'm perfectly aware of nitric oxide sensors for measuring all nitric oxide on the breath in asthmatics, and there they have to filter, and that's a very humid, let's say, environment, and they do have to take out the humidity. The question is NO2 cross sensitivity? It's interesting actually, because when I think about a carbon monoxide sensor, it's not sensitive to so much to carbon dioxide. So I suspect it's pretty similar, that nitric oxide would not necessarily be sensitive to nitrogen dioxide, and I would use the carbon monoxide and carbon dioxide sensors as a sort of predicative example of why that was actually a true statement. How large can sensors be? These sensors can be absolutely tiny. I mean, making a sensor package the size of, a finger is really of no issue. The power drawn, it's obviously when you're trying to predict the power drawn on a device that you have not yet made, I've just kind of put some conservative numbers here that it might be 15 milliwatts to 210 milliwatts. I'm laughing at myself because it's basically an order of magnitude, so I give myself a good error budget there. Until you make it, and well, really, until you sit down with engineers and actually really design it out, you don't absolutely know. These sensors most of our sensors, especially in this case, I think they could be in a gas flow or in still gas, essentially in a sort of in a still gas, or I don't say stagnant, but I don't think it needs to necessarily be flowing. And if it I think it's really just mechanical engineering as to what the gas flow above that sensor is. The sensor itself is probably doesn't care that much. The sensor at some point has to be housed just in terms of ruggedness. But I think housing is just really a little detail on the back of, the big questions are, can you make the sensor in the first place? What's the drift? What's the offset? What's the cross sensitivity? Those are the big questions. Then the rest of this is just, I want to just suggest engineering, but it's fairly trivial. We often work on micro projects, mini projects, proof of concept, so people can engage with us that way. If I've put any links, and I've definitely put the links underneath the video as well. Slight change of course now. So I'm coming off gas sensing, specifically on nitric oxide, and now I'm moving over to making electrical connections on gold sensors. So I appreciate somebody was kind and they bought some gold sensors off us. They sent us a question that said, well, how do I solder onto this? Really, I don't want you to solder onto it, because I have seen people soldering onto sensors, and they're individually dropping, little wires and soldering on. It's really a waste of your time. You just need a connector. And so in this particular case, they have what we call a gold 303. So they need a connector that takes a 7mm connector. And we have this in several flavors. These are banana plug, female banana plug receptacles. And we do it in 2, 3, and 4mm. So there's a 2mm version, a 3mm version, and a 4mm version. I wish I'd put a link to this. But if you're on a PalmSense Biologics or an Anapot, then you're probably using 2mm. If you're on Autolab or CH Instruments, you probably need a 4mm. Be really careful. Check the banana plugs beforehand, just in case for some reason you've got some strange flavor of cables. But you do need a 7mm, I suspect, you need a 7mm SPE connector, and probably it's either 2 or 4mm depending on the potential stat that you have. If you don't have good connection, this is actually the same sensor. One of them was same sensor tested with a poor connection, with a good connection. When you have the good connector, and in this case we actually ended up making a connector for this person, they got really nice data. When they had a poor connection, it really did. They really did get some really distorted data. So it is important that you connect, and that's why I really don't like the idea of soldering. It's too time consuming. It's nice and low cost, but you're trading essentially your time for money. Just get a connector. And because if you solder badly as well or damage the pieces, it's a bit of a nightmare. Question number 3 about sensors for water and soil. It's probably worth saying that we have quite a long history in soil sensing. This is one of our facilities in the UK, and we can see that we have done kind of these soil stacks. In fact, when I look at these soil stacks, I can see they're really instrumentized in terms of this. There's all sorts of sensors sticking into these soils, and I can also see that we've actually we've got things like drain taps at the bottom, so you can see that we're sort of pouring nutrients in from the top. We often have sensors at different levels, and then we're sort of able to measure the progression of water and nutrients down through the stack. So we've got quite a long history. And the reason we have kind of things like 4 stacks is because one of the things I go on about a lot at ZP is that we've really instrumentized testing. What I mean by that is we just do a lot of parallel testing. You can't just test one sensor at a time. You really have to kind of instrumentize and have a lot of data. In fact, when I look at the shelf at the back here, I can actually see that he's got a parallel set up there, so he can actually make lots and lots of measurements. Anyway, we have a long history of measuring things in the soil. Now, we obviously specialize in nutrients, sort of potassium, phosphate, ammonia, things like such things. That's a slightly closer shot. This is some nitrate data that we did with JIC and LPB, and we were testing the sensor at different concentrations, because we were kind of coming from that in those days that how would I say this? Because we were coming to this from a medical perspective. We were using kind of things like millimolar. We soon learned and started going into ppm or kilograms per hectare, for example, but we were testing like we were chemists. The nitrate sensor really progressed. People sometimes ask us, for example, was that sensor able to be used in water applications? And the answer was yes, because we were actually testing it primarily in water at the beginning. Before then, it became sort of more robust. Like I say, we did this with JIC and LPB in the UK, but we did all the engineering and obviously all the manufacturing, etc., and all the science as well. Well, when I say science, we are very good at making. In fact, here's an image here. A lot of our sensors are made by printing technologies. I have a long background from the glucose strip world, and so we're sort of taking that kind of technology and fabricating new types of sensors upon it. In this case, in conjunction with JIC and LPB, we were putting this sensor to the soil level here, and then putting these sensors at depth within the soil. We've really instrumentized and send this data these days to the kind of clouds. So we have the rods were in the ground. The rods have connectivity to one another. So we're sending the data along a chain of rods to a base station, and then up to something called Julie. I haven't got much slides today on Julie, but Julie is a database from Zimmer and Peacock. You can sort of go Julie, if you Google Zimmer and Peacock and Julie, it's Julie with a DJULI. It's got an API built into it, an application program interface, so we can send, whether we're talking medical today or we're talking water sensors, and if we make a sensor and the sensor electronics, we can send that data to the cloud and process it there. We don't just do the stuff in the lab, so that lab sort of setup was just a precursor to actually going out and sticking sensors in the field. I'm not going to dive into the data today, but this is something that we did with a large agro-tech company, and also in conjunction with LPB and JIC. We put these sensors in the soil and sort of measured the nitrate for several months. And we collect all sorts of interesting data, including rainfall as well. And we really got a great feedback on how the sensor was actually able to really guide the addition of nutrients in that particular application. It's probably worth saying that we're particularly interested in environmental monitoring. I think this is more of a comment. This thing about agriculture, environmental monitoring, or water monitoring. If I contrast this with the medical industry, in the medical industry, the need is really sort of urgent. People want these sensors because they want to sort of sort out a health problem. When you try to kind of sort out things like environmental problems, people become a little bit more reluctant to purchase. So I think most of what we do, if you want to develop technologies in the kind of environmental, agricultural, or water industries, you have to sort of get some sort of EU funding on that. Otherwise, who's the payer? There is an eventual payer. I agree that actually nitrate fertilizer prices were peaking at about 1,400 euros per ton. I'm not quite sure where they are today. I know that was exceptional. It was linked to COVID-19, linked to various unfortunate wars causing energy prices to come up. So I do see the return on investment, but what you do find is if you want to do the R&D, you have to find a payer. And for us, we often find the EU or is quite, and government agencies are quite good payers for that kind of work. So I will change direction slightly now and talk about our pH sensor. So this is somebody was curious about our pH sensor. I mean, they're right here. So they say solid state, and a lot of the sensors that you see from us, they're not your traditional ion selective electrode where, there's a sort of barrel device and there's some electrolyte or some liquid or some gel inside it. No, they're solid state, including the sensors that we were talking earlier on about the agricultural application. Anyway, but they went in particularly want to know, can we detect pH 2 and lower? If there's a link, then the link's already underneath the video. And the quick answer is we have got data on the website that shows us testing at pH 2. So here in this data stream, if you go to that link, you'll find this data, pH 2, pH 2, pH 2. I think we may have tested on pH 1, but essentially you'd have to sort of buy it and try in your particular liquid. I mean, pH 1 is, quite acidic. But I can at least demonstrate that we've done pH 2. So you did specifically say pH 2, so yeah, we can do pH 2. Lower than pH 2 would be pH 1.9. I'm still sure we'll be fine with pH 1.9, but you do have to characterize it in your particular sample type. Question number 5. We do have a video about how to do R&D with our uric acid sensor. So this is Andre, and he made a video quite a while ago for us. So if you go to this page, you'll find Andre talking through actually taking the anapot, which I've also linked to, and actually making uric acid measurements. So do go to this page, watch the video. What we tend to do is we tend to support sort of our academic colleagues by putting out a lot of free information. We also have workshops as well. So, watch the videos and get a sense from it there. If you're really stuck, one of the best ways of learning or getting your questions answered is come to one of our workshops. We have quite large groups now from universities actually come to our workshops. It's quite surprising because we charge for the workshops, but it's really nice that we get like 4 people turned up from one department to a workshop in Coventry. So it's nice that people do come to our workshops. So I've put a link to the workshops in 2023 that we've so far organized. If you want a workshop and maybe there's a geographical location you can suggest or a date, just get in contact with us and let's figure it out. Design of a custom electrode. So we do get a lot of people requiring, a part of what we do is screen printing. I mean, this really goes back to, the fact that, most glucose strips on the market are screen printed. It's a good way of making low cost biosensors. Anyway, they want 3 working carbon electrodes, which is completely fine. With dimensions of 1 millimeter by 4 millimeters, which is completely in line with our hypervalue electrodes. They want them separated by 2 millimeters. 2 millimeters is a good distance because it's close enough so you can pack everything in, but it's not so close that you kind of have a lower yield. They want to separate working electrodes by 1.5 millimeters. They want the reference electrode on there, counter electrodes. Again, the dimensions are all pretty good, and they want to keep it fairly small, which is good because essentially the smaller you make these sensors, the higher the production density. They also want a particular color, which is completely fine. They really wanted to discuss their design. I agree. So I think the best way of starting is actually just to open up a micro project with us. I think in that micro project we'll go through the spec, do an initial do some concept designs, and then if there's some budget, start making some screens. So I think engage in a micro project there. We always have extra free information for people. So that in relevance to this particular one, there's actually a link here that I think is relevant. I just want to talk about technologies for CGM, continuous glucose monitoring, and lactate monitoring. It's probably worth saying that when we make our biosensors, especially our enzyme sensors, we often use a barrier layer. If you order it, it does come with instructions of use. There's also some videos online as well, and also storage conditions. People always get really spooked by our storage conditions because we always kind of say keep in the fridge and all this kind of stuff. Well, you have to, people like us would obviously lean on caution, but there are storage conditions in there. It does help. A barrier layer is important in both glucose and lactate monitoring. I'd even say even more so in lactate monitoring, because lactate enzymes often have a lower enzyme activity, so you do have to kind of filter the lactate a lot more in order to kind of get linearity. On the 8th and 9th of February 2023, we will be having a workshop in Horton where everyone gets to make and test glucose sensors. We discuss measuring lactate in sweat and things like that. So I really, it's very, there is a background to CGM lectures, but there's also a lot of hands-on lab work as well, including making sensors, testing things like lactate sensors, seeing our clean room. We have a very good clean room for the assembly of CGM sensors. It's not only clean, but it's also aseptic as well, because many of our sensors actually get implanted into human bodies. And I think that is actually an excellent workshop, and I've put a quick link to that workshop there. Also, I mean, our lactate formulation for activating lactate sensors is pretty similar to our glucose one. Not exactly the same, but similar. And it's orders of magnitude more expensive because the materials are just orders of magnitude more expensive. And I've put a link to that product as well. As I say, I think one of the best ways of familiarizing yourself with this is actually to come to one of our workshops. It's a good question, this one. This question was actually about plastics in biosensors. This is definitely something that we all know that, disposable forks, cups, plates made of plastics, it's just not going to be acceptable. Now, at the moment, there's not that much discussion about, well, what about disposable glucose strips or disposable biosensors? I think biosensors have to have a disposable element to them because they often come in contact with, things like blood, and if you try to reuse blood products that have been in contact with blood, it's an exposure risk, not necessarily to the person who's originally used it, but everyone else in their household or everywhere else in the environment. So there has to be some idea that if something's got contaminated with a biological fluid, then it is, unfortunately, has to be disposed of. Now at ZP, we actually are aligned with the UN sustainability goals. We had a in-house vote. Everyone got to vote at the time. And from that, we found that, as a company, we wanted to be aligned with good health and well-being, which was super useful because we're in the medical space. Clean water and sanitation, which is really useful because actually, many of our sensors are getting transferred over to the environmental, let's say, applications. Climate action, I would actually say that, if anyone who's working on we have worked on measuring nitrate in soil. 1.2% of global CO2 comes from nitrate production. Life below water, anything that, for example, if any technologies that reduce nitrate usage in farming, you are absolutely helping life below water. eutrophication of the water systems is a real problem. So it's not, we're just lucky that what we actually do can actually help the environment and society so much. I think it really comes down to a fundamental that if you want to improve anything, you have to measure it. Well, when you're a sensor business, by nature, you're able to measure things, and therefore, if you're measuring um, things like in the blood or things in water or things in the soil, then you are going to help improve it. So you can actually then be part of improving this situation. So fortunately, the things that we care about are also things that we can actually help solve. Back to the question, which is, if you look at the UN Sustainability Goal number 12, it's responsible consumption and production. And I would actually suggest that the question here is it responsible to be producing medical diagnostics in plastics, knowing that they would potentially be used once and disposed of? At the moment, ethically, I think we're okay. But I actually, at ZP, we are definitely thinking this through, actually. And at the moment, um, there's not much political pressure on, let's say, the industry. But, we are definitely thinking about how to make sensors out of biodegradable material. So it's not ignored. At the moment, there's no particular political pressure, but I think it will come. And obviously, any innovative company wants to be thinking about it now, and we definitely are. Little link to our stance on the UN sustainability goals as well. Question number 9. Somebody is interested in our methylene blue screen printed electrode. Just for anyone's interest, things like methylene blue are quite useful. Sometimes we're using things like dehydrogenase enzymes. This questioner isn't interested in a dehydrogenase enzyme, but they just want to know what's the they actually want to know quite a lot of information, but I can only give you what I can give you, or rather what I'm wanting to give you. So we have a methylene blue working electrode. It's there's a lot of carbon content in that electrode, so that's what I can say. The other electrodes around it are silver chloride, so we have a silver chloride reference and the silver chloride working electrode. It's unusual that the counter electrode rather is silver chloride, but it's actually it's actually advantageous. It's really been thought through. So if you're interested, I've put a link to that below. So let me say thank you, and I should really have done a quick summary of the questions, but this week we've talked about NO sensors. We really have to develop it, but we have already done the carbon monoxide sensor in the past. We've also covered, a barrier layer, I would say, would improve. It generally helps the linearity on both glucose and lactate. I think it would actually help even more so on lactate. And the rationale for that is that lactate enzymes often have a lot less sort of activity per sort of, milligram, if I could say. So you do have to you can't load them up with a lot of enzyme activity. We've also covered on sensors for example, environmental applications. And I know I made a few comments there, but it's a difficult market because everyone can see the problem, but it's also finding the sort of person who is able to fund those kind of developments is quite tricky. And the success that we have had in the past is through government funds and funding. I've also talked about make good connections to your gold electrodes, otherwise it will end up distorting your data, and it'll be, it's a bit of a shame otherwise. The pH sensor, you can see that we've got data down to pH 2 anyway. And I think that sort of covers up most of what we were doing this week. So let me say thank you very much to Hitchem and Martin, and I appreciate the questions that come in this week. If you have any questions, Zimmer Peacock, I should put, in fact, here's a contact here. So just go to contact support and we will be happy to answer questions. I wish everyone a good week, and I will speak to some of you by email, I'm sure, during the week. Okay, thanks very much.